everyone, so this is the next lesson all about motion graphs. You've probably dealt with graphs before, so we're just going to talk about how it applies in physics and in science in general. So, for the most part, if I asked you to calculate the slope of displacement versus time and I gave you this data, you'd probably be able to get something like this. Now, as you know, taking the slope is change in y over change in x. So we take 2 points on the y-axis, 2 points on the x-axis, take the difference, and divide them. When you do this, you would get 2. Now, if you also take into account that these numbers have units, these numbers are measured in meters, the numbers on the y-axis, and the numbers on the x-axis are measured in seconds, then you would notice that this unit would end up being meters per second. Meters per second, that means velocity. So it turns out that when you have a displacement versus time graph and you take the slope of it, you end up getting a velocity. Now, this actually makes a lot of sense because if you recall, slope, as I just pointed out, the equation is change in y over change in x. So it's y divided by x. The equation for velocity is displacement divided by time. So you end up having y displacement, displacement's on the y-axis. You have x as time, times on the x-axis. The equation is identical. Another way to think about this is that whenever you're looking at slope and determining whether or not slope is the right one, think about whether or not the equation deals with division or not. If you have a graph like this that's linear, then when you take the slope of it, you end up getting a constant graph like this. So a linear increasing displacement graph means a constant non-changing velocity. This is extremely important as a lot of people tend to misconstrue what the graphs mean. You have to be able to look at a displacement graph and be able to know what that refers to as to a velocity. Don't make the mistake of reading a displacement graph as a velocity graph and thinking that this means that it is speeding up. That is not what this means. Now, let's say we had the opposite. Let's say we had a velocity graph and I wanted to know, could I take what is the opposite of taking the slope? Taking the slope went from displacement to velocity. What brings us from velocity to displacement? I could do the same trick where I look at the equation and in here I look at the equation v equals d over t. I move things around and I get that d equals v times t. This is multiplication. How do I do multiplication with a graph? Area. So in order for me to actually get a displacement graph, or sorry, displacement values from a velocity graph, I would instead use area. That is what is considered the opposite of taking the slope. Now, if you take in calculus, you may know the fancy way of saying this. Taking the slope, the fancy way of taking this in calculus is taking the derivative, and the opposite of a derivative is an integral. And for those, like I said, taking calculus, you may know that as being a fancy more complex area. So the area underneath the graph gives us displacement. You make a little shape. You take length. In this case, it didn't show it, but this is supposed to be a constant graph. So I make this into a rectangle. It's length times width, and I get my displacement. So taking the slope goes from displacement to velocity. Taking the area brings us back from velocity and gives us displacement. If I end up having a just quick note, if I have a displacement graph that is constant, then my velocity graph should be 0. You want to be able to know what the graphs are going to look like. You need to be able to know if I have any type of displacement graph, what should the velocity graphs look like? If I give you a complex graph like this, you should be able to determine what the velocity would look like. You split it up into each segment. You look at each segment individually. You can pinpoint which segments have a positive velocity, zero velocity, or negative velocity, and you can pinpoint exactly, calculate the exact value based off of the values provided. Now, let's say that we wanted to actually come up with a displacement graph. Now, this one's a little bit trickier. The way you're supposed to do it is take little segments, or the way you could do it is you take little segments, find what the values are, and essentially plot those points on a displacement graph and connect them with a line. Since we know that a linear displacement gives us a constant velocity, then we know that the graph for displacement should be linear. Now, if I instead had a velocity that was linear, so it went up like this, my displacement is going to look a little bit different. Here, I'm making a triangle, so I do half base times height. I do the same thing, And you'll notice that the values or the points will constantly go up. So a curved graph like this for displacement comes from a linear velocity. Now, is there another way that we can, determine these slopes? Determine what the graph for velocity should look like based off the displacement graph. The way that you would do this is by using your hand and just making it tangent to your graph. When your fingers are pointing up, that means that the slope is positive. When the fingers point down, it's negative. And if your hand ends up being flat, it's zero. Um, so, for example, if you had a graph that looked like this is your displacement graph, because taking the slope is essentially just finding lines that are tangent at that point. If you put your hand up against this graph, you would find that it's pointing downwards on this left-hand side. So we'd have a graph that starts, our velocity graph would start negative. As we trace around here, my hand flattens out here, so that means my graph should go to zero. And then as it goes up, it goes positive. So this would be my velocity graph, starting negative, going to zero, and then going positive. And because this is a curved graph, I know that my velocity graph should be linear. The same thing applies for the other type of curved displacement graph. Again, my hand would be pointed up, meaning positive slope or positive velocity. My hand flattens out, which means it's zero, and then it goes down, meaning it goes negative. Now, what if we instead do velocity? What if we had the slope of velocity? What would we get? Would we get displacement? No. Same thing we should do as we did before is look at the units. If you look at the units, you find that you end up getting meters per second squared because we do velocity divided by time. Meters per second divided by another seconds gives us meters per second squared. So taking the slope of velocity gives us acceleration. This is a very nice diagram that I recommend looking at. When you have displacement and you take the slope, you get velocity, and when you take the slope again, you get acceleration. Every time you take the slope, you're adding on another seconds in the denominator. So you have meters, meters per second squared. As you go backwards, you take the area and you get rid of one of those seconds. It is extremely important that you know when you look at a graph whether to take slope or area. And it's actually extremely important that when you look at a graph, that you get into the habit of saying that I either have to take slope or area because chances are those are going to be the two things that you're going to do. Anytime you make a graph or you're provided a graph, you're going to either take the slope or take the area. It's very rare that you would do any sort of calculations. I'll show you some of the few examples where that's not the case. But you want to get into this habit because if they're giving you a graph, you want to use the graph. Now, one interesting thing, this is a little extra tidbit, is that you can actually get equations from these graphs. For example, this is a linear graph. Uh, the equation for a line is y equals mx plus b. On the y-axis, we have velocity. On the x-axis is time. So I could replace y with v and x with t. The slope we already talked about is acceleration, so I could replace the m with acceleration, and the y-intercept, where it starts off here, well, that's just the initial velocity. So from the equation of the line, y equals mx plus b, I get v equals v naught plus at, the acceleration equation. Same thing here, this is a quadratic equation. The equation for a quadratic is y equals ax squared plus bx plus c. On the y-axis, well, that's displacement. The x-axis time. So if I replace y and x with d or d and t, I end up getting that. The c term, that's my initial position. So that's actually x naught. And then we end up having a and b. What is a and b? Well, that just turns out to be the v naught and 1/2 at squared. So technically, if you know the equation of your displacement curve, and you know what the coefficients from the x squared and x are, you can figure out what the initial velocity and the acceleration are. And same thing with a constant line, y equals mx plus b, x equals v naught, vt plus x naught, right? So again, another way of showing that we get the annoying x equation. This is pretty much it for the motion graph questions. Like I said, you really do need to know how to take the slope and area of something, but you need to know what you get when you do that and get into the habit of uh, going that route anytime you see a graph. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.